Hello, everyone. If you're just joining us, a quick reminder that you can submit questions using the questions tab at the top of your screen. We'll take as many questions as we can at the end of the presentation, and if we don't get to your question, don't hesitate to send it to webinar@neo4j.com, and we'll have someone follow up with you. Be sure to post about today's event using hashtag Neo4j or hashtag Neo4j Connections, and you'll be entered to win some cool Neo4j swag. And now I'll turn it back over to Lance Walter to introduce our next session.
Thanks, Marilee. Like many of our enterprise customers in industries like healthcare and financial services, critical information often lives in unstructured or semi-structured formats in the government industry. And here too, graphs can help. Gary Mann is a field engineer here at Neo4j and has been with the company for going on 3 years. He's got many years of experience in technical sales, having worked at leading companies like AppDynamics and Securonics, as well as IBM, working on the Watson team with a focus on big data. Gary has a bachelor's degree in computer science from Penn State University, as well as an MBA from Carnegie Mellon and Tepper School of Business. Let's use Neo4j for document discovery with our own Gary Mann. Welcome to Connections, Gary.
Thanks, Lance. As Lance said, my name is Gary Mann. I'm a federal solutions engineer working mostly with the US federal government. And today, what I wanted to talk about was a use case that we've been hearing a lot and getting a lot of traction with customers. And it's document discovery with graph data science. So what I wanted to do is sort of walk through some slides, talk a little bit about the use case, describe where it is a good fit for graphs, and show a quick demonstration of actually how we might create a document discovery graph and enhance it with graph data science with the Neo4j Graph Data Science Library, and then work through a little sample application. So some of the things that we're hearing from customers are that they're already very good at search. And traditionally, document discovery and document search is a use case that search engines are typically focusing on, and not necessarily graph databases. But customers are telling us they actually have too much data. They have too many tools that already do the same things. They have a lot of search tools, and they're very good at search. They also have a lot of different types of data that's very variable. Some data has certain attributes, some data does not. So they really need something that's schemaless, that can adjust as the data flows in different formats and in different types with different attributes. And one of their main problems that they're telling us is that they need to focus their analysts. So analysts have all these tools, they have all this data, but they really need tools that actually focus them and guide them along a path. And one thing they're also saying is that they have unstructured data, and they view that as just a starting point. They view search as the first step, and then their analysts really want to start with a search and then traverse and discover paths through the data. So typically our customers have both unstructured and structured data, and the relationships between those different pieces of data are very important. And so that's where Neo4j comes in. The context and the relationships and how these entities interact is really a great fit for a graph database. So the customers actually want to navigate and traverse across both the structured and unstructured data, either visually as well as textually. So that's really the use case here for a graph data discovery. And here are some things that are why graph is a good fit for this type of use case. So Neo4j is a flexible and schemaless model. You can apply some elements of schema, but for the most part, we're schemaless. We're able to handle a lot of varying types of data. Neo4j supports unstructured queries, and typically that's an entry point into the graph. We allow pattern matching and the ability to traverse relationships and understand how data is related. Pathfinding is a big use case within this type of application, where people want to understand how entities are related. How is a person related to a vehicle? Something like that. And then the last item is the graph analytics. So once you have your data in the graph, there's a lot of different things you can do with it to enhance the graph and add value into the graph to support the analytical process. So what we're going to do in today's demo is apply graph analytics to this graph so that we can really enhance it and allow analysts to leverage all the data. So just the last point is graphs can really form a basis for a lot of different use cases, a lot of different analytical use cases. And these are just some of them for what we're hearing from customers, just plain discovery, analytics, investigations, fraud, money laundering, a lot of different use cases in federal government that are focusing on this type of application. So I mentioned graph algorithms here. So I like this slide because these are the sort of the two different ways of looking at data in a graph. On the left-hand side, we've got local patterns where we're issuing just standard queries and leveraging the structure of the graph to understand and get insights into things. So think about traversing a relationship from a person to a vehicle to another person that may drive the same vehicle. That's all local patterns, and you can do that through standard Neo4j querying mechanisms. On the right-hand side are graph algorithms, and graph algorithms sort of take a higher level view at a graph and leverage the relationships at a top level and do sort of a global computation and looking at the overall structure and how these nodes and relationships are interacting in the graph. So the key point for graph algorithms is, you're looking at things at a high level and not just doing pattern matching. So when you combine both local patterns and graph algorithms together, you can really get some powerful analytics in a graph. And these are some of the questions you can answer with local patterns as well as with global analytics. Local patterns are, how is X related to Y? Who's driving this car? Who has access to this car? Who is this car registered to? Those are all local patterns. How are this person and this person related to each other? And that could be through multiple hops in a graph. It could be up to 5, 6, 7, 8 hops in a graph in order to find out how these two people are related through a graph. What characteristics do two entities share in common? Those are all local patterns. And this is an example here of a Cypher query that explores a local pattern. So from a graph analytics perspective, we're looking at things at much higher level. And we're saying, what are the most important entities in my graph? What data is related through its relationships in the graph? Looking at the structure of the graph, how is data related to each other? And the last one is, can I predict relationships that don't really exist in the graph based on the existing structure of the graph? So those are all different things you can do with graph analytics. And what we're going to do is we're going to explore some of those in our demonstration. This is the Graph Data Science Library. I'm not going to step through each one of these algorithms, but we're going to leverage a few of these today in our demonstration. The key point is that Neo4j supports 50+ algorithms in the Graph Data Science Library. And what we provide is a workspace where you can project your graph into a workspace, apply analytics to it, and then write back the results of those analytics into your graph. And by writing back, those could be writing relationships, new relationships that might not exist in your source data, or attributes to a node or to a relationship that, again, don't exist in your source data. The algorithms we're going to focus on today are going to be community detection, similarity, and centrality and importance. So those 3 algorithms we're going to focus on today for our demonstration. But just a key point is that, with 50+ algorithms, you really have to understand your data and understand what you're looking to do with the data. And then you can define sort of a recipe for how you apply the Graph Data Science Library to that underlying graph. One thing we're not going to show today in the demo, but I just wanted to point out to you, is that Neo4j Graph Data Science Library recently introduced supervised machine learning capability. And that's focused on link prediction and node classification. So if I have a data set and I train a model based on that data set in the graph, I can then use that on new data to predict links, to predict relationships that may not be there in the source data. I can also use a trained model in Neo4j to classify nodes that I don't understand what this is when new data is introduced into the graph. So those are two key capabilities that came out recently in the Graph Data Science Library. So today for our example use case, what we're going to do is we're going to ingest some data from just a public data source. It's the National Highway Transportation Safety Administration. Maintains a database of complaints that people file on their cars. And these could be safety issues, it could be mechanical issues or reliability issues that people file against their vehicles. And what we're going to do, and it's a great data set because it's got both an unstructured and a structured component. So we're going to ingest that into a graph. Then we're going to leverage some graph analytics to enhance that graph and support the data in the discovery process. We're going to enable unstructured search on the graph using Neo4j's out-of-the-box full text index. And then we're going to enable visual exploration through that graph using Neo4j Bloom. We're going to tie it all together in a simple web application. So that's going to be our demo for today. And this is what it's going to look like. So at the bottom, we've got your local patterns and your global computation. You got your input data feeding into Neo4j. At the top, on the left-hand side, if some applications might require a dashboard to summarize data. In the middle, we've got our exploration capability with Bloom, and on the right is a custom application. So what we're going to show today is focusing on exploration and the custom application and how you can tie that all together today in a demo. So now I'm going to jump into a demo that talks about how we set this all up. So I'm switching here. So the first thing I'm going to do here is jump into the Neo4j browser. And what I have is I have a simple playbook that steps through, sort of the process that we use to create this example graph. And what I did was to save time is I already loaded the data into the graph. You can see we've got about 117,000 nodes, about 720,000 relationships in the graph already. Because loading the data is actually not super important for purposes of this demo. So we've got here, the first thing we're going to do is create indexes. We've already created those indexes as we loaded the data, but I did want to show you that that's a necessary step. The second step is we're loading data here. And this data set's fairly large. I think it's got like 1.8 million complaints. So we focused it down a little bit. We were just mostly interested in vehicles. And I think we focused it just for the last few years, more recent type of car models out there. So it's just a tab separated file that we load. And as I indicated, we already loaded the data, but this is the load script that we could step through in a larger demo. So after we load the data, this is kind of what this is what the schema looks like. It's very simple here. We've got reports in the middle that people are filing about a vehicle. The report is also about a component of the vehicle. Maybe they're complaining about the seatbelts, maybe they're complaining about the brakes or something like that. And then we've got a manufacturer that manufactures that vehicle. So some of the analytics we might want to understand are what are the commonalities between reports? What are people saying about, say, a Chrysler vehicle? Those kind of interesting commonalities that we can explore and traverse in a graph. So one thing we noticed when we loaded the graph is we noticed that there was a lot of duplicate data in the graph. And so what we did was we used the Neo4j APOC library here to compute a fingerprint on the report nodes and to kind of refactor those and merge those together. And that's a key thing. A lot of times what happens is the data set that you're ingesting into the graph is not necessarily the final data set that you want to work with in the graph. So here we're making some adjustments to resolve duplicates and merge those together. So a very simple step. We've already sort of done that in our pre-work here. So the next step, again, that we've already sort of pre-staged, but we want to take the unstructured text from the reports and apply some very simple natural language processing to it to enable to add into the graph. So what we're doing is we're extracting terms and noun phrases from what people are complaining about. So if somebody's saying, "Hey, the steering on my Ford Tempo stopped responding while I was on a highway," we'll parse through that, and we want to understand what the key phrases are. So there's a lot of different options for doing NLP processing. We provide some APOC procedures that can reach out to commercial vendors on AWS, Google, or Azure to pull in, pass in text, and then pull back all the entities and actually create a graph out of that. But there are several open source mechanisms to do, including Python libraries, or even a Neo4j procedure that you could apply. So what we're doing today, as you can look, we have just a simple Python service that is just taking the text and it's returning terms and noun phrases from that. And what we've actually done, and we're leveraging the APOC library to query that from within the graph here. And again, we've already done that. So this is actually what the schema looks like right now. So we've got the existing schema that we loaded, and now we have reports that have terms associated with those that are extracted out of that unstructured piece of data. So the next thing we want to do is we actually want to start analyzing the graph with graph data science. And this is really the sort of the goal of this demo here. So the first thing I want to do is I want to look at the terms, and I want to understand how influential they are in the graph. So we're applying here an article rank algorithm to the terms in the graph, and we're going to apply a score called term rank to those terms. And so the idea is you could actually, everybody's probably familiar with PageRank from sort of the search world. This is a similar algorithm that's based on PageRank. And what we're doing is we're trying to understand which terms are the most important based on the structure and the relationships in the graph. So I'm just going to run this very quickly here. And what it's doing here is it's parsing through, and it finished writing a score to each one of the term nodes in the graph. And we're going to use that score later on to understand how different terms are related to each other in the graph and do some analytics. So that's pretty important to understand what terms are more important than others, because if you actually looked into the graph, you're going to see some very common terms like car or vehicle or something like that. So we want to understand what terms are important. The next thing we're going to do is we're going to work through some node similarity. So that's a key thing within document graphs, is trying to understand what nodes are similar to other nodes. And by similar, I mean, how do they look from a graph standpoint? Do they have similar relationships? Are they connected to the same nodes? So we're looking at things from that standpoint. And so the first thing we're going to do here is we're going to create a graph in the Graph Data Science Library's in-memory graph catalog. And we're going to project from the underlying Neo4j graph just these nodes. So we're going to project reports, terms, vehicles, and components, and these relationships. So the key point is, and that was very quick, you can see how many nodes we projected, how many relationships we projected. And the key point is that this is going into an in-memory catalog that then we can operate on with our graph algorithms. And that makes the graph algorithms run very quickly. They're running on an in-memory resident representation of the graph, and it, it it really enhances the ability to process very large graphs with the graph algorithms. So this step is actually going to take a little bit of time. I think it takes maybe about a minute here. So I'm gonna run the node similarity algorithm, and if you can see what it's going to do is it's going to write a similar relationship with a score associated for all the different similar nodes it finds. So I'm going to run that, kick it off here, and we're going to let that run a little bit. It may take a little while. The next thing I could do is I could stream the results in real time. So we have an in-memory resident graph. I could run node similarity stream, and in this case, I'm pulling back the top 10 results, or 10 results sorted by however I want to sort them. So that's another avenue we could do, but we're not going to do that since we're already doing the writing here. So once we finish the writing side of things, and we're going to keep an eye on this as it keeps running, this is what the scheme is going to look like. We're going to have a similar relationship here between different reports. And that's fairly, we're going to leverage that relationship in our graph. And that similar relationship is actually going to have a score associated with it. So now we can see that this finished. And we compared 27,000 report nodes. And we've got about 135,000 relationships written. So that's pretty good, I think. So let's take a quick look and see what we did. The other thing, before we do that though, the other thing to point out is that there's different ways to approach the same problem. Different algorithms, there's multiple node similarity algorithms within the graph data science library. There's multiple centrality algorithms. So you have to actually think about which ones apply best to your use case here. This is an alternate approach where we can just take in real time, we can actually, on a per query basis, just try to understand through a Jacquard similarity algorithm, which nodes are related to which reports are similar to which. And what this is doing is just looking for term co-occurrence here. So if I run this, we get back graphs, and you can see we're agreeing to some degree with the similar relationships that we've already written on these reports. So it's actually fairly interesting that there's different approaches to the same thing. But for purposes of our application, we're going to leverage the node similarity that we just wrote, that algorithm that we just executed here. And we can query it here. So I'm going to issue a query. I'm going to return some top 10. And you can see, here we have somebody complaining about a broken valve spring caused the engine to shut down. And then here we have some other text complaints that we're identifying as being somewhat similar to that. So it's kind of interesting to see how it's determining that similarity. And it's based on the terms that we've extracted, based on the vehicle, and based on the component that we've identified. So we're going to leverage that in our analytical demo. The next thing we want to do is we want to identify communities of documents. And it's a similar process here with one key difference. So we're going to create another in-memory graph here. But what we're going to do, and we're going to include some of the same node types here in there, but we're also going to try and leverage that term rank that we created a few slides ago. And we're going to leverage that into this community graph to influence the communities. And if a node doesn't have a term rank, which some of these aren't going to, we're assigning it a default score of 60, which falls kind of right in the middle. So we're going to create that in-memory resident graph there. There, it created it. It's got about 117,000 nodes. Just one thing to point out about this too is this is a cipher query. So there's different ways to project your graph into the analytics workspace. And this way we're using Cypher in order to do that. And it gives you a lot more control over which nodes you want to project and how you want to project them. So there's definitely different approaches there. Or you can do a native projection, which is what we did for the node similarity, which is just projecting all the nodes of a certain type and all the relationships of a certain type. So now that we have a projection for communities, we're going to run a community detection algorithm. And here I'm going to stream it first and get back 10 results here. And notice how I'm using a weight property of the rank that we projected. So you can see we've got a bunch of different communities. I think I'm sorting by the size of the community. So we've got some very big communities here. And then we go down to some smaller ones that we're understanding here. So what Neo4j is doing, what the Graph Data Science Library is doing, is it's kind of parsing through, running this algorithm to try and understand how these reports are related to each other and whether they fit together into the same community. There are multiple community detection algorithms also available within the Graph Data Science Library. So now we're going to go through and we're going to write that. We're going to write a community attribute. And we just ran through it, ran fairly quickly. So now we've got a community attribute. And we can query. We can even query based on similarity. So here I'm going to say, give me some reports that are in the same community based on this one report. So what we've got here is we've got two reports that we're identifying as being in the same community as this source report. So it's just another way to sort of understand how data is related. And we've really enhanced the graph by applying these algorithms now. So there's a couple other things you can do before to really enhance it. We're not going to do it for purposes of this demo, but you can identify influential topics. You can show top topics on a report, and all that information can get fed into your analytical application that you're going to expose to analysts and users to actually leverage this data that's in the graph here. So we've applied several different algorithms here. We've actually already enabled full text search within Neo4j, but we're going to enable, we have full text search indexes that are based on a Lucene underlying library. So all the power and sort of the different analyzers that come with Lucene, we can leverage within Neo4j to provide a full text search experience as well. So what I'm going to do now is I'm going to jump in to our sample application here. And this is a very simple web-based application that we created, just some HTML, some JavaScript, to provide a front end to allow somebody to really leverage and explore that graph that we just created here. You notice at the top, we've got just two tabs here. We've got search, which is what we're seeing here. And then we've got Bloom here. So let me reload this. Let me verify. Sorry. So I'm going to make sure I'm logged into Bloom here. And the first thing I want to do too is, since I thought I had it, but I'm going to import my perspective here, and I'm going to use it. So in Bloom, a perspective is sort of how you visually see the information in the Bloom application here, and it kind of controls the colors and all the different, the captions. So I'm gonna select that for my report caption. So all that's controlled via Bloom. So what I'm gonna do is I'm gonna, in my search application here, I'm gonna search for the term break here. And you can see down here, we executed a full text search. I've got several issues that are coming up. I think I'm posting 10 results here. And then we've got these different tabs over here. And this is where we really want to leverage the analytics that we just ran on the graph. So we've got this one and say, hey, give me all the similar documents to this one here. So I just clicked on that, and now we have related reports here that are just based on the analytics that we ran. At the top, we've got the most influential terms that are talked about in this results set here. So with break, obviously people are mentioning problems, highway, failure. That's concerning, right? So there's a lot of different information you can get from that. So we're leveraging the article rank that we ran earlier on the graph here. And the other thing I really want to do here is I want to explore this. Hey, I've got a great document here. I want to explore this in Bloom. So I'm just going to explore. So I'm going to explore this. There we go. I'm going to explore that report in Bloom. Now I've got this report here. I drill in. I start to see the captions that I've defined here. And it happens to be a GMC Sierra. And then I want to identify. I can even I want to find out what things people are complaining about here. Now I see service brakes, engine are those components. Maybe I want to expand out all the different terms that people are mentioning as part of that complaint. And so what we're seeing now is we're seeing that an analyst can now traverse. Maybe they're interested in brake failure lights, and I want to see what other vehicles, what other reports have that issue. So now I've expanded that out, and I see this is a Honda now, where somebody has actually reported a brake failure light issue in their unstructured report. So it allows the analyst to sort of traverse those paths now visually. Notice how I started with a search and I jumped into Bloom and I'm exploring this visually. And that's a key thing here. So if I go back to my search here, maybe I want to do other types of exploration here. So I've got a different Bloom icon here. Maybe I want to explore directly some similar documents here in Bloom. So I'm clicking in there. And now, again, I've got my Denali, I've got the different similar documents here, and I can explore from there. I've got a Chevy Silverado. I can open up the terms that are affiliated with that. So one of the other things I think is interesting about Bloom is notice how all the terms are colored orange. I could actually set a little rule here, which I think is kind of interesting. And I'm going to set it based on the rank that we computed. And I'm going to set it to be, and if you notice, here's the midpoint and the range. I'm going to apply a color, a gradient color, based on how we've ranked those terms, which are most important. And so that's kind of interesting. So brake failure, steering. So these are the issues that are really coming to the forefront here based on what we're seeing. So you have a whole set of rules that you can apply to sort of cue the analyst visually, which is, I think, key. So a couple other things I want to do is I want to, maybe I want to explore the communities that I've identified. So each one of these reports may be in a community. So I'm gonna click into that and I'm gonna explore the community here. And one of the things interesting about this view is that this community label doesn't really exist in our source graph. It's a projection. It's a virtual node that we created, and then we're kind of associating the different reports that are in the same community. And notice how these reports are all against the GMC Sierra Denali. And so that's interesting. And so our algorithms, identified that those 3 reports as belonging in the same community. One other thing I want to do is maybe I want to explore the tags themselves. So if I can click one of these tags here, and I can also explore that in Bloom. I'm trying to think of a good one. I don't know, maybe steering is a good one here. So I'm going to click on that. I'm going to explore that in Bloom. And so that's a term, steering, that then I can then, I'm not going to blow this up to 2,400 nodes here, but you could do that and you could visualize those all directly on Bloom. So that's just a very high level overview of this sample application that we've created. So I want to jump back into the slides just to kind of wrap it up and handle questions. So the key takeaways here are that data relationships are key. So many customers are now realizing that they really have relationships between different pieces of data. They've got both structured and unstructured data. Other types of data stores or search engines or databases can't really represent the problem in context as well as a graph database can. And it's all about exploration and analytics. So enhancing your graph to allow your analysts and your mission users to really be led along a path and to be highlighting key pieces of data so that they can very quickly zero in on what they're looking for by focusing them along paths. And then the graph data science algorithms really can enhance that graph. So the key thing is that once you have this document in a document graph in a graph database, you can use it as the basis of many discovery and analytical use cases, not just a single one. So it's available to all or many different types of applications. So that's what I had here. Thank you, and I think I will take a few questions.
Great, thank you so much, Gary. That was such a great demo, and I have to say, Bloom demos are always my favorite for sure. So we've received some questions from the audience, and I want to let the audience know that if they do have a question, they can submit it via the questions tab located at the top of the screen. And if we don't get to your question, someone from Neo4j will reach out to you directly, or you can also send an email to webinar@neo4j.com and we'll get you pointed in the right direction. But here's one that asks, I have 20 million documents. Can GDS scale to support the analysis of that type of document set?
Yeah, that's a great question. So GDS is specifically designed to handle high scales of data. So by projecting a graph into memory and then applying the algorithms in memory with multiple parallel threads, we can scale to the billions of nodes. So yes, definitely GDS is designed to scale. Typically, you need a different type of server with more memory in it to support that kind of scale, but absolutely. And a key point for GDS too is when the data is projected into the in-memory workspace, it's compressed. So it's really trying to take advantage of the available memory on the server to be as efficient as possible.
Great, thank you for that explanation. And here's one that's saying, I see you're using Bloom within your application, my favorite. How difficult is it to integrate Bloom with my web application?
Yeah, so this was just an example of how you can embed Bloom into another application and jump back and forth between Bloom and maybe a custom web application. So Bloom does have certain entry points. In this case, what we were doing is leveraging the Bloom query interface, which is just via URLs, and you can send in Bloom searches and tell Bloom to execute that search and present the information to the user directly on the screen. So we've embedded Bloom in a couple different applications similar to what you saw today. And we're continually adding capabilities to Bloom to enable, to really support embedding it into larger applications. So definitely doable.
Great. And here's a follow-up question to that. So if someone wanted to share, some of those visualizations from Bloom, how would they go about doing that?
So Bloom has the ability to share perspectives. So I can share how the colors and those kind of things, so different users can collaborate on the same perspective. And we also have the ability to enter in a presentation mode and download a screenshot of a visualization that describes something that you want to show to another person. And again, Bloom is continually adding ability to share visualizations in different ways. So I expect more of that in the future.
Oh, great. And I know we're getting a little tight on time, but I want to throw this one out there. So where can someone go to find more information on GDS?
Yeah, so there's a couple different places, and let me jump into. So we have a couple different places out there, but just on the Neo4j website, we offer 2 books that you can register and download. One that a lot of people already know about is this O'Reilly Graph Algorithms book that was originally written by 2 of our Neo4j experts. And you can register here and download a free copy of this book. There are also blogs and sandboxes that are available through the Neo4j website that allow you to sort of experiment with the GDS algorithms and explore kind of what they can do. And then if you're familiar with Neo4j Desktop, there's actually a desktop application, Graph Data Science Playground, which is a little application that runs on Neo4j Desktop that allows you to sort of explore how these algorithms work with your underlying graph and really learn a lot about the algorithms and how they're applied.
Great, thank you for that information. And we are about out of time. So Gary, I want to thank you for your time today. It was a super informative demo. And I want to thank the audience for their time as well. Our next session will be starting in just a few minutes, so stay tuned for that. Thanks so much.
Thanks, everyone.